All right, today we're going to peel back the layers on the AI brain and look at something absolutely critical, the activation function. You can think of it as the secret sauce, really. It's what takes a neural network from just a simple calculator to a powerhouse that can make incredibly complex decisions.
So, what is that secret? How does a machine actually learn to do things like recognize your face, or understand what you're saying, or even compose music? Well, the answer is kind of wild. It's all thanks to millions of tiny mathematical decision makers all working together. And that's exactly what we're going to unpack.
Okay, so here's the game plan. We'll start with what an activation function even is, and then get into why they're so ridiculously important. We'll walk through the whole family tree of these functions, give you a practical guide on which one to use and when, and then we'll take a quick look into the future. Sound good? Let's jump in.
All right, first things first, let's break down this idea. What exactly is an activation function? What is this so-called decision maker sitting inside a neuron?
Okay, picture a single neuron in a network as let's say a gatekeeper at a club. It's getting all this information from other neurons, right? It adds it all up, and then it has to decide, is this important enough to let through? The activation function is basically the rule book that gatekeeper uses. It's not just a simple yes or no. It's more like a dimmer switch. It decides how much of the signal gets to pass on to the next neuron in line. Super important.
So, you might be wondering, why do we even need this gatekeeper? I mean, why not just let all the information flow freely? Well, it turns out, if we did that, our super powerful AI brain would be, well, kind of dumb.
And this slide just lays it all out perfectly. Look, without activation functions, a neural network is just a linear model. That's it. You could stack 1,000 layers, one on top of the other, and it would still just be doing the equivalent of basic linear regression. It would be totally useless for learning the messy, complex, nonlinear patterns of the real world. But you add these simple little mathematical gates, and bam, suddenly the network gets depth. It gets the power to actually understand things like language and images. It's a total game changer.
So, to really hammer it home, they introduced that critical nonlinearity we just talked about. They also keep the neuron's output in a nice, manageable range, and, this is a big one we're about to get to, they help stop major training problems in their tracks. They are, and I'm not exaggerating here, the very reason deep learning gets to be deep.
Now, here's where it gets interesting. Not all activation functions are the same. In fact, their history is this really cool story of evolution, where each new function was basically an attempt to fix the problems of the one that came before it.
So back in the day, we had the classics, Sigmoid and Tanh. The big idea was pretty simple. Take any number, no matter how big or small, and just squeeze it into a nice, predictable range. Sigmoid would squish everything down between 0 and 1, which is super handy if you're talking about probabilities. Tanh did the same thing, but between -1 and 1. They were the pioneers for sure, but they both shared a critical, almost fatal flaw, a problem called vanishing gradients.
And this was the big bad villain of our story. Seriously, imagine you're whispering a secret down a long line of people. By the time it gets to the end, it's just a garbled mess, right? The vanishing gradient problem is a lot like that. As the learning signal tried to travel backward through a really deep network, it got smaller and smaller and smaller with each layer, until it basically disappeared. It just vanished. This meant the earliest layers of the network completely stopped learning. It was a huge roadblock for AI.
And then along came our hero, ReLU. It stands for Rectified Linear Unit, but don't worry about that. The idea behind it is almost laughably simple. ReLU's rule is this: if the number coming in is positive, just let it pass right through. If it's negative, just make it 0. That's it. This one simple trick was incredibly fast, and, most importantly, it solved the vanishing gradient problem. This right here is what unlocked the modern era of deep learning.
But like any good hero, ReLU had a flaw, an Achilles heel, if you will. Because it just zeroes out any negative input, a neuron could get knocked into a state where it only ever got negative inputs. And if that happened, it would only ever output 0. Its gradient would be 0, and it would basically die. It would just stop learning forever. This became known as the dying ReLU problem.
So the community did what it does best. It innovated. They came up with this really smart refinement called leaky ReLU. And the idea is just as simple. For positive numbers, it's exactly the same as ReLU. But for negative numbers, instead of squashing them to zero, it allows a tiny, non-zero value to leak through. Just a little bit. And that tiny, tiny change was enough to keep the neuron alive and learning. It was the perfect patch for our hero's biggest weakness.
Okay, that's a lot of theory, I know, but it's a cool story, right? So now let's get down to brass tacks. How do you actually pick the right tool for the job when you're building something?
Think of this as your quick start guide or a cheat sheet. For all those hidden layers deep inside your network, your default go-to choice should be ReLU. Just start there. It's the standard for a reason. It's fast and it just works. Now, if you start running into issues with dying neurons, that's your cue to switch over to leaky ReLU. Simple. Now for your final output layer, that's where it gets specific to your problem. If you need a simple yes or no answer, that's a job for Sigmoid. If you're trying to choose between multiple options, like cat, dog, or bird, you'll use something called Softmax. It's perfect for taking a bunch of scores and turning them into probabilities that all add up to 100%. And finally, if you're just trying to predict a number, like the price of a house, you don't need anything fancy. A simple linear function is all you need.
And here are a few classic mistakes you'll want to avoid. Please, whatever you do, don't use the old-school Sigmoid or Tanh in your deep hidden layers. You're just asking for trouble with vanishing gradients. Second, Softmax has one job and one job only, the final output layer. Don't use it anywhere else. And of course, always make sure that final activation function actually matches the kind of problem you're trying to solve. It's a common slip-up.
So as you can see, this whole story of evolution is definitely not over. The hunt for the perfect activation function is still very much on, and it's leading to some really cool new ideas.
I mean, researchers are constantly coming up with new functions. The big state-of-the-art models you hear about all the time, like the transformers that power things like GPT and BERT, they often use even more advanced functions with names like Swish or GLU. We don't need to get into the weeds on how they work, but what they do is combine the best parts of all the functions we've talked about to squeeze out every last drop of performance. It just goes to show you that this tiny fundamental piece of AI is still a massive area of innovation.
And that kind of leaves us with one final big question to chew on. We've seen how these pretty simple mathematical rules allow an AI's neurons to make decisions. But as AI gets more and more sophisticated, moving beyond just recognizing cats in photos to understanding things like nuance and sarcasm and creativity, what kind of decisions will its neurons need to make then? And what new functions will we have to invent to even make that possible?